It's impossible, isn't it? Our minds aren't built to comprehend absolute nothingness. We live in a universe so full of structure, so rich with form and pattern, that emptiness itself becomes a concept we can barely grasp. But this is where our story begins, or rather, just after it begins. Because 13.8 billion years ago, something happened. The universe burst into existence in an event we call the Big Bang, and in those first fractions of a second, everything that would ever exist was born, not in its current form, of course, not as stars and planets and galaxies, but as pure potential, as the raw ingredients waiting to become something more. Welcome. I'm glad you're here. Tonight, we're going on a journey back to the very beginning of cosmic structure. We're going to explore how the first galaxies formed, how chaos and simplicity transformed into the breathtaking beauty and complexity we see when we look up at the night sky. This is a story about transformation, about how gravity and time and the peculiar properties of matter work together to build islands of light in an ocean of darkness. It's a story that's still being written, still being discovered, with new chapters emerging from telescopes that can peer further back in time than ever before. So settle in, get comfortable. Let the weight of your body sink into whatever surface supports you. This journey will take us through billions of years, but we have all the time we need. There's no rush. There's no test at the end. Just let these ideas wash over you like gentle waves, and if you drift away at any point, that's perfectly fine. The universe waited billions of years for galaxies to form. We can afford to be patient too. The primordial darkness. In the beginning, after the first blinding flash of creation, the universe was remarkably simple. For the first few minutes after the Big Bang, it was so hot and dense that matter as we know it couldn't exist. Subatomic particles crashed into each other at incredible speeds, creating and destroying themselves in an endless dance of energy. But as the universe expanded, it cooled, and as it cooled, the first atomic nuclei began to form in a process called Big Bang nucleosynthesis. Imagine a cosmic kitchen where only the simplest recipes are possible. In the first few minutes, the universe created hydrogen nuclei, just single protons. It created helium nuclei made of 2 protons and 2 neutrons bound together. And it created tiny trace amounts of lithium. That was it. That was the entire menu. 3 elements, with hydrogen making up about 75% of all matter, helium making up about 25%, and lithium barely registering as a rounding error. These primordial elements, forged in the first moments after creation, would remain essentially unchanged for hundreds of thousands of years. But these nuclei, these bare atomic cores, couldn't yet capture electrons to become proper atoms. The universe was still too hot, still too energetic. Free electrons zipped around at tremendous speeds, and any time one tried to settle into orbit around a nucleus, a high-energy photon would come along and knock it loose again. Light couldn't travel freely through this soup of charged particles. Photons would scatter off free electrons constantly, bouncing around like pinballs, going nowhere. The universe was opaque, filled with a glowing fog that prevented light from traveling more than a short distance in any direction. This continued for about 380,000 years. Let that sink in for a moment. 380,000 years where the universe was nothing but this uniform, featureless plasma. No structures, no variations, just an endless expanse of hydrogen and helium nuclei swimming in a sea of electrons, all glowing with the heat of creation. If you could have been there, you wouldn't have been able to see anything beyond the glowing fog immediately around you. You certainly wouldn't have predicted that this uniform soup would someday organize itself into trillions upon trillions of galaxies, each one containing billions of stars. But time has a way of revealing hidden potential. As the universe continued to expand and cool, it eventually reached a critical temperature, about 3,000 degrees Kelvin. At this temperature, something remarkable happened. Electrons finally slowed down enough to be captured by atomic nuclei. Protons captured electrons and became hydrogen atoms. Helium nuclei captured electrons and became helium atoms. This process, called recombination, transformed the universe almost instantly on cosmic timescales. Suddenly, within just a few thousand years, the universe went from opaque to transparent. Light could finally travel freely. The photons that had been trapped, scattering endlessly off free electrons, were released. They began their journey through space, cooling and stretching as the universe expanded, eventually becoming the cosmic microwave background radiation we can still detect today, a faint whisper of that moment when the universe first became clear. But here's what's crucial to understand. When we say the universe became transparent, we don't mean it became filled with light in the way we think of light. Yes, there was radiation everywhere, the afterglow of the Big Bang itself. But there were no stars yet, no galaxies, no bright, shining objects to illuminate the cosmos. The universe had entered what scientists call the cosmic dark ages, a period that would last for another 100 million years or more. Think about what that means. Imagine the entire universe stretching for billions of light years in every direction, filled with nothing but neutral hydrogen and helium gas. No fusion reactions burning in stellar cores. No supernovae exploding and seeding space with heavy elements. No quasars blazing with the power of supermassive black holes. Just darkness, cold, expanding darkness, broken only by the gradually dimming glow of the Big Bang's afterglow. Yet even in this darkness, in this apparent emptiness, something was happening. The universe wasn't quite as uniform as it appeared. When we study the cosmic microwave background, when we look at that snapshot of the universe as it was 380,000 years after the Big Bang, we can see tiny variations in temperature and density. These variations are incredibly small, just 1 part in 100,000. But they were there, subtle ripples in the fabric of space and time itself, seeds planted during an even earlier epoch of cosmic inflation. These tiny density variations, these barely perceptible differences from one region to another, held the key to everything that would follow. In regions that were slightly denser than average, even by the tiniest amount, gravity had a little more material to work with. And gravity, patient and persistent, never stops pulling. It doesn't care how long it takes. It doesn't tire or give up. It just keeps drawing matter together, slowly but inexorably, amplifying those initial tiny variations. Breathe with me for a moment, in and out. Feel the air moving through your lungs, the oxygen nourishing your cells. That oxygen was forged in the heart of a star that died billions of years ago, but we're not there yet in our story. We're still in the darkness, still in that patient time before the first stars ignited, and in that darkness, unseen forces were at work. The invisible architects. To understand how the first galaxies formed, we need to talk about something strange, something that makes up most of the universe, but that we cannot see, cannot touch, cannot directly detect in any ordinary way. We need to talk about dark matter. Dark matter is one of the most profound mysteries in modern physics. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact with electromagnetic radiation in any way we can detect. In fact, it seems to interact with ordinary matter only through gravity, and yet we know it must exist because we can see its gravitational effects everywhere we look. Galaxies rotate in ways that only make sense if they're embedded in massive halos of invisible material. Galaxy clusters bend light from background objects through gravitational lensing, revealing far more mass than we can account for with visible matter. The entire large-scale structure of the universe requires dark matter to explain how it formed. Scientists estimate that dark matter makes up about 85% of all matter in the universe. Let that settle in your mind for a moment. Everything we can see, every star and planet and nebula, every galaxy blazing across the cosmic void, all of it combined represents only 15% of the matter that exists. The rest is dark, invisible, known to us only through the gravitational fingerprints it leaves on the things we can see. Now, here's where dark matter becomes crucial to our story of the first galaxies. In the early universe, right after recombination, ordinary matter, what physicists call baryonic matter, was very hot. It had kinetic energy. It had pressure. These properties meant that it couldn't simply collapse under its own gravity, at least not immediately. The thermal pressure, the random motion of atoms bouncing off each other, resisted gravitational collapse. This is why it took so long for the first stars to form. But dark matter was different. Dark matter, by its very nature, doesn't have these complications. It doesn't interact electromagnetically, which means it doesn't experience thermal pressure in the same way. It doesn't collide with itself. It doesn't radiate energy away. From the moment after the Big Bang, when the universe became cool enough for dark matter particles to move relatively slowly, dark matter could begin clumping together under gravity without anything to stop it. Picture it this way. Imagine you're trying to herd cats and dogs into a pen. The cats, being cats, scatter in every direction, resist your efforts, climb over fences, do everything possible to avoid being corralled. That's like ordinary matter in the early universe, resisting collapse through various physical processes. But imagine the dogs are sleepwalkers, unaware of anything except a gentle pull toward the center. They slowly, steadily drift together without resistance. That's dark matter, responding only to gravity, patiently collecting into clumps. In the hundreds of millions of years after recombination, dark matter began forming structures called dark matter halos. These halos were regions where dark matter had collected into gravitationally bound clouds, held together by their own mass. They started small, perhaps containing just 1,000,000 times the mass of our sun, and grew over time through mergers and accretion, slowly gathering more and more material. Here's the beautiful part. These dark matter halos acted as gravitational wells, like invisible basins in the fabric of space-time. And as the universe continued to cool, as ordinary matter lost energy and slowed down, it began to fall into these gravitational wells. Hydrogen and helium gas, the simple primordial elements forged in the Big Bang, started collecting in the centers of dark matter halos. And there, Finally, conditions would become right for something new to happen. Without dark matter, galaxy formation would have been very different, perhaps impossible in the timescales we observe. Dark matter provided the gravitational scaffolding, the framework onto which ordinary matter could attach and organize itself. It's still there today, surrounding every galaxy we can see, including our own Milky Way. Current estimates, based on gravitational measurements, suggest that the Milky Way's dark matter halo contains somewhere between 600 billion and 3 trillion times the mass of our Sun, significantly dwarfing the visible galaxy itself. Think about that as you lie there. You're on a planet orbiting a star in a galaxy embedded in an enormous halo of invisible matter. We're surrounded by this mysterious substance held in its gravitational embrace, and yet we can't see it, can't touch it, can barely prove it exists, except through careful measurements of how visible matter moves. It's a humbling reminder that our senses reveal only a small slice of reality, that the universe is far stranger and more wonderful than what we can directly perceive. The dark matter halos that formed in the early universe came in a hierarchy of sizes. The smallest ones, called mini-halos, contained only about 1 million solar masses. Larger halos could contain 10 million, 100 million, eventually billions of solar masses. And crucially, the mass of these halos determined what kind of structures could form inside them. Smaller halos could only cool their gas through molecular hydrogen, which limited how efficiently they could form stars. Larger halos had more options for cooling, which meant they could form stars more readily. This is important because it means that galaxy formation wasn't uniform across the universe. Different regions, depending on their dark matter halo mass and their local conditions, would begin forming stars at different times. Some regions would light up early, while others remained dark for hundreds of millions of years longer. The universe didn't flip a switch from darkness to light. It was more like a slow dawn, with islands of light appearing here and there, gradually growing and spreading until the entire cosmos was illuminated. In computer simulations of cosmic structure formation, when scientists model the behavior of dark matter over billions of years, they see it naturally organize into a pattern called the cosmic web. Dark matter forms dense nodes where galaxy clusters will eventually reside, connected by filaments where galaxies line up like beads on a string, surrounded by walls or sheets of slightly less dense material, all enclosing vast voids where almost no matter exists at all. This cosmic web structure is one of the most striking features of the universe, visible in galaxy surveys that map the positions of millions of galaxies across vast stretches of space. And this structure, this intricate web, began forming in the darkness of the early universe, built by the invisible hand of dark matter's gravity. The first galaxies would form preferentially in the densest nodes and along the filaments, guided by dark matter's unseen architecture. Let yourself rest with that image for a moment. An invisible web spanning the cosmos, woven by gravity over hundreds of millions of years, waiting for ordinary matter to fall into its embrace and light it up with the first stars and galaxies. The first stirrings. As the universe aged beyond its first 100 million years, conditions were slowly becoming right for something extraordinary. The dark matter halos were growing, merging, collecting more mass. The ordinary matter, The hydrogen and helium gas was cooling and falling into these gravitational wells. But for stars to form, something more specific had to happen. The gas had to cool enough and become dense enough that gravity could overcome the outward pressure and cause collapse. This is where the physics gets delicate and beautiful. When gas falls into a dark matter halo, it heats up. This might seem counterintuitive, but it's a consequence of gravity's work. As particles fall inward, their gravitational potential energy converts to kinetic energy, to motion, to heat. So even though the universe as a whole is cooling, gas falling into halos actually gets hotter. For star formation to occur, this gas needs a way to shed that heat, to radiate it away and cool down. In the modern universe, in regions where stars are forming today, gas can cool in many ways. Heavy elements like carbon and oxygen can absorb energy and re-emit it as infrared radiation, efficiently carrying heat away. Dust grains can do the same. But remember, in the early universe, there were no heavy elements yet. No carbon, no oxygen, no dust, just hydrogen and helium. This limited the cooling mechanisms available. The primary cooling mechanism in the early universe was molecular hydrogen, H2. This is not the atomic hydrogen we usually talk about, where each atom exists independently. Molecular hydrogen is two hydrogen atoms bonded together into a molecule. And crucially, molecular hydrogen can rotate and vibrate, and these rotations and vibrations can absorb energy from the gas and radiate it away, not very efficiently, especially at low temperatures, but enough to matter. For molecular hydrogen to form, hydrogen atoms needed to find each other and bind together. This happened most readily on the surfaces of free electrons and negative hydrogen ions floating through the gas. It was a slow process, inefficient by modern standards, but over millions of years, enough molecular hydrogen formed in the densest regions of dark matter, halos, to make a difference. Here's where we encounter something called the Jeans mass, named after the British physicist James Jeans. The Jeans mass is the minimum mass of gas cloud that can collapse under its own gravity given a particular temperature and density. If a clump of gas is less massive than the Jeans mass, thermal pressure will push it apart. If it's more massive, gravity wins and the clump collapses. The Jeans mass depends on temperature. The hotter the gas, the higher the Jeans mass, the more mass you need before gravity can cause collapse. In the modern universe, in regions like the Orion Nebula, where stars are forming today, molecular clouds can cool down to about 10 degrees Kelvin, incredibly cold by everyday standards. At these temperatures, the Jeans mass is relatively small, which allows many individual stars to form, including stars with masses similar to our Sun or even smaller. But in the early universe, molecular hydrogen cooling couldn't get gas much below 200 degrees Kelvin. That's still cold by human standards, but it's much warmer than modern star-forming regions. And this higher temperature meant a higher Jeans mass. The minimum mass of a collapsing gas cloud in the early universe was much larger than today, perhaps 100 times larger or more. This has profound implications. It means that the first stars couldn't be small. They couldn't be sun-like. The physics simply didn't allow it. The first stars forming from primordial gas in the first dark matter halos had to be massive, perhaps 30 times the mass of the Sun, perhaps 100 times, perhaps even more. Some theoretical models suggest the first stars could have been several hundred solar masses, true monsters compared to the stars we see today. Breathe slowly as you contemplate this. The universe had to start big. It couldn't form delicate structures first. It had to begin with giants, with massive stars that would burn bright and hot and fast, living only a few million years before exploding in spectacular supernovae. And these first stars, these cosmic pioneers, would be the ones to fundamentally transform the universe, to end the Dark Ages and begin the epoch we call Cosmic Dawn. In computer simulations of the early universe, scientists can model this process in detail. They start with the conditions revealed by observations of the cosmic microwave background, all those tiny density fluctuations. They include dark matter and its gravitational effects. They include ordinary matter and its physical properties, its ability to cool, to heat, to respond to pressure and gravity. Then they let the simulation run forward in time, watching how structures form. What these simulations show is that the first stars likely began forming somewhere between 100 and 200 million years after the Big Bang, though pinpointing the exact timing remains challenging, not everywhere at once, but in scattered locations where conditions were just right. These first stars formed in small, dark matter halos, mini halos containing perhaps 1 million solar masses of dark matter. Into these mini halos fell enough ordinary matter to form stars with masses measured in tens or hundreds of suns. The gas would have collected at the center of the halo, forming a dense core. As it collapsed under gravity, it heated up, but molecular hydrogen cooling kept it from getting so hot the collapse stopped. The core became denser and denser, hotter and hotter, until finally, at the very center, the temperature and pressure reached the threshold needed for nuclear fusion to begin. Hydrogen nuclei started fusing into helium, releasing tremendous energy. A star was born. Imagine the moment. After hundreds of millions of years of darkness, a point of light appeared in the void, the first star burning in a universe that had never seen light from fusion before. It would have been alone at first, a single brilliant point in an ocean of neutral hydrogen gas, but it wouldn't remain alone for long. Birth of the cosmic pioneers. The first stars, what astronomers call population 3 stars, were fundamentally different from any stars that exist today. Their metal-free composition, their enormous masses, their extreme brightness, all these factors combined to make them unlike anything we can directly observe in the modern universe. Let's talk about what made them special. First, their composition. Remember, these stars formed from gas that had never been processed through previous generations of stars. It was pure primordial material, roughly 75% hydrogen, 25% helium, with only trace amounts of lithium. No carbon, no oxygen, no iron, none of the heavier elements that we take for granted in stars like our sun. This pristine composition affected every aspect of their physics. Without heavy elements, these stars couldn't generate energy through some of the fusion pathways that modern stars use. They relied primarily on the proton-proton chain, the same basic fusion process that powers our sun, but at much higher temperatures and pressures due to their enormous masses. The lack of heavy elements also affected their opacity, how easily light could escape from their interiors. Metal-free stars are more transparent to radiation, which affects their structure and evolution. Their masses, as we discussed, were enormous because of the higher Jeans mass in the early universe. Theoretical models suggest typical population 3 stars might have had masses between 30 and 300 times the mass of the Sun, though we haven't yet observed these stars directly to confirm this. Some models even predict they could have been larger. These predicted masses would put them squarely in the category of supermassive stars, objects we never see forming in the modern universe. Large mass means extreme luminosity. A star's luminosity, its power output, scales steeply with mass. According to stellar evolution models, a star 100 times the mass of the Sun might be 1,000,000 times more luminous. These first stars would have been extraordinarily bright, pumping out vast quantities of energy in the form of ultraviolet radiation. They would have been hot, with surface temperatures likely exceeding 50,000 degrees Kelvin, making them appear blue-white to any hypothetical observer. But here's the trade-off. The more massive a star, the shorter its lifetime. Our Sun will live for about 10 billion years, slowly and steadily fusing hydrogen in its core. A star 10 times the mass of the Sun might live only 20 million years. A star 100 times the mass of the Sun would burn through its fuel in just a few million years. The first stars, these population 3 giants, were cosmic mayflies, burning brilliantly but briefly. When these stars ran out of hydrogen fuel in their cores, they didn't gently fade away like lower mass stars. They were so massive that they continued fusing heavier and heavier elements in their cores, building up layers like an onion. Hydrogen fusing to helium, helium fusing to carbon and oxygen fusing to neon and magnesium, all the way up the periodic table, creating elements with each new fusion stage until the core was made of iron. Iron is special in the cosmic scheme of things. It's the most stable nucleus, the endpoint of energy-producing fusion. Fusing iron into heavier elements doesn't release energy, it requires energy. When the core of a massive star turns to iron, fusion stops, and without fusion to generate outward pressure, gravity wins. The core collapses catastrophically in less than a second, falling inward at 1/4 the speed of light, reaching nuclear densities where protons and electrons combine to form neutrons. The collapse halts suddenly when the core reaches neutron degeneracy pressure, and the rebound sends a shock wave racing outward through the star. This shock wave encounters the infalling outer layers and explodes them into space. We call this a core collapse supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. These supernova explosions were pivotal events in cosmic history. They marked the deaths of the first stars, but more importantly, they were the forges where heavy elements were created and distributed into the universe. During the explosion, intense neutron fluxes bombarded nuclei, building elements heavier than iron through rapid neutron capture. The blast wave swept up surrounding gas and enriched it with all the elements from carbon to uranium. The pristine hydrogen and helium of the early universe was now contaminated, seeded with metals, as astronomers call any element heavier than helium. But population 3 supernovae did more than just enrich the gas with heavy elements. They also released tremendous amounts of energy into their surroundings, heating gas, pushing it around, creating blast waves and turbulence. This energy injection could actually inhibit star formation in some regions, while triggering it in others by compressing gas clouds. The universe was becoming more complex, more dynamic, no longer just steadily cooling and collapsing, but now alive with violent, energetic processes. Perhaps most significantly, the ultraviolet radiation from population 3 stars began ionizing the hydrogen gas around them. Remember, the universe had been filled with neutral hydrogen since recombination about 400 million years earlier. Now, for the first time, that hydrogen was being split back into protons and electrons, reionized by starlight. Around each massive star, a bubble of ionized gas began to grow, expanding outward as photons streamed from the star's hot surface. Let your mind drift to that scene. A massive blue star, thousands of times more luminous than our sun, surrounded by an expanding sphere of ionized gas. The boundary between ionized and neutral gas would have glowed with the light of hydrogen emission, a vast nebula light years across. Multiple stars forming in the same region would create overlapping bubbles, their ionized regions merging together. Slowly, gradually, the universe was lighting up. These ionization fronts, the boundaries where ionized gas met neutral gas, were dynamic, constantly shifting interfaces. Photons from the star would race outward at the speed of light, encountering neutral hydrogen atoms and splitting them apart. But behind this ionization front, protons and electrons would occasionally recombine, temporarily returning to neutral hydrogen before being ionized again. It was a constant tug-of-war between ionization and recombination, with ionization gradually winning as long as the star continued to shine. The size of each ionized bubble depended on several factors. A more luminous star produced more ionizing photons, creating a larger bubble. A star in a lower density region had less hydrogen to ionize, allowing its ionizing radiation to reach further before being absorbed. And crucially, the lifetime of the star determined how long the bubble could grow. Population 3 stars, despite their tremendous luminosity, lived such short lives that their ionization bubbles might have grown to only a few hundred light years in radius before the star died and stopped producing ionizing radiation. When a population 3 star died in a supernova, the explosion itself had profound effects. The blast wave raced outward at speeds of thousands of kilometers per second, heating gas to millions of degrees. This superhot gas emitted X-rays, which could ionize hydrogen much more efficiently than ultraviolet light, extending the ionized region far beyond what the star's radiation alone could achieve. The mechanical energy of the blast wave could also push gas around, compressing some regions while evacuating others, creating complex structures in the distribution of gas. The heavy elements ejected by the supernova didn't spread uniformly through space. Some material was ejected at very high speeds and traveled far from the explosion site. Other material was slower and stayed relatively close. This created an inhomogeneous distribution of metals, with some regions becoming enriched quickly, while others remained nearly pristine for much longer. This patchiness and metal enrichment would have profound consequences for where and how the next generation of stars formed. The light from these first stars could travel much farther in ionized gas than in neutral gas. In neutral gas, ultraviolet photons are absorbed by hydrogen atoms, but in ionized gas, once all the hydrogen is already split into protons and electrons, photons can travel freely. This meant that as more stars formed, as more regions became ionized, light could spread more easily from one region to another. The universe was becoming transparent to starlight, emerging from the darkness. Scientists call this process cosmic reionization, and it represents one of the major phase transitions in cosmic history. Based on multiple lines of evidence, the universe transitioned from neutral to ionized between about 150 million and 1 billion years after the Big Bang. It wasn't instantaneous. It didn't happen everywhere at once. Observations suggest it was patchy, irregular, with some regions reionizing early while others remained neutral for hundreds of millions of years longer. But eventually, the entire universe was reionized, filled with ionized hydrogen plasma, much as it is today. Rest now for a moment. Feel the weight of time pressing on these events. Hundreds of millions of years passing, each year containing 365 days, each day containing 24 hours. Stars being born, living their short lives, exploding, seeding the universe with new elements. The inexorable march from simplicity toward complexity, from uniformity toward structure, from darkness toward light. The dawn of light. The epoch of reionization, spanning from roughly 150 million to 1 billion years after the Big Bang, was a time of profound transformation. It's tempting to think of it as a simple switch, darkness suddenly becoming light. But the reality was far more gradual, far more interesting. Let's walk through what actually happened, step by step, as the universe emerged from its dark ages. Picture the early universe at 100 million years after the Big Bang. The first population 3 stars have begun to form in scattered locations. These locations aren't random. They're determined by where dark matter halos reached sufficient mass to trap and cool gas. The universe is still mostly dark, mostly filled with neutral hydrogen. But here and there, in isolated pockets, stars are shining. Each of these stars creates a sphere of ionized gas around itself. The size of this sphere depends on the star's luminosity and the density of the surrounding gas. For a typical massive population 3 star, the ionized region might extend for tens or hundreds of light years. That sounds big, but remember, galaxies are measured in thousands of light years, and the distances between these first stars were even larger. Most of the universe remained neutral. As time passed, more stars formed. Some formed individually in small dark matter halos. Others formed in small groups or clusters where multiple halos had merged or were close together. In these denser regions, the ionized bubbles from multiple stars began to overlap. Instead of isolated spheres, you'd have irregular, interconnected volumes of ionized gas, expanding outward as more stars continued to form. The key to understanding reionization is to realize that it's a balance between ionization and recombination. Ultraviolet photons from stars split hydrogen atoms into protons and electrons, ionizing the gas. But protons and electrons can also recombine, forming neutral hydrogen atoms again. In low-density regions, recombination happens slowly, so once the gas is ionized, it stays ionized. But in high-density regions, recombination is faster, which means you need a continuous supply of ionizing photons to keep the gas ionized. This created a complex dynamic situation. The universe wasn't simply marching from neutral to ionized in a uniform way. Instead, there was a constant battle between ionization and recombination, with the ionized region slowly winning as more and more stars formed and added their ionizing photons to the mix. Scientists have studied this process using several different methods. One is to look at the spectra of very distant quasars, supermassive black holes that shone brightly in the early universe. When light from a distant quasar travels to us, it passes through all the hydrogen gas between the quasar and Earth. Neutral hydrogen absorbs light at specific wavelengths, leaving dark lines in the spectrum. By studying these absorption lines, astronomers can map out where neutral hydrogen existed in the early universe. What they find is fascinating. At redshifts around 6, corresponding to about 1 billion years after the Big Bang, the universe was highly ionized. Most of the hydrogen was in ionized form, but at higher redshifts corresponding to earlier times, the absorption increases dramatically. Some quasar spectra show what's called a Gunn-Peterson trough, a complete absence of light at certain wavelengths because all of it has been absorbed by neutral hydrogen. This tells us that before about 900 million years after the Big Bang, significant amounts of neutral hydrogen still existed. Another way scientists study reionization is through the cosmic microwave background. When the universe was ionized, free electrons could scatter cosmic microwave background photons, leaving a subtle signature in the microwave radiation we detect today. The WMAP and Planck satellites have measured this signature with high precision. The results suggest that the universe was substantially reionized by about 400 million years after the Big Bang, earlier than the quasar observations alone would suggest. This apparent discrepancy is actually telling us something important. Some researchers have suggested that reionization was a complex, extended process with possibly multiple phases. One proposed scenario is that population 3 stars caused an early phase of reionization between 200 and 400 million years after the Big Bang. Then, as these massive stars died and stopped forming as prolifically, some regions may have partially recombined. Finally, a second wave of star formation in the first galaxies may have completed the reionization process more permanently. However, this remains an active area of research. The James Webb Space Telescope is providing new insights into this era by observing galaxies that existed during the epoch of reionization. JWST can study the sources of ionizing radiation directly. Early results show that there were more bright galaxies in the early universe than expected, which helps explain how reionization could have proceeded as quickly as it did. These galaxies were remarkably efficient at producing ionizing photons. Think about what the universe looked like during this transition. If you could somehow observe it from outside, you'd see a network of glowing regions, ionized bubbles expanding and merging, connected by filaments where more stars were forming, separated by dark regions where neutral hydrogen still reigned. Over hundreds of millions of years, the glowing regions grew and connected until the entire observable universe was lit up, filled with ionized plasma. The end of reionization didn't mean the end of structure formation. It was really just the beginning. With the universe now transparent to ultraviolet light, radiation could travel freely, affecting gas clouds across vast distances. Models suggest the pressure of this radiation could heat gas, potentially preventing it from falling into smaller dark matter halos and forming stars. This may have shut down star formation in the smallest halos, helping to ensure that only larger structures could continue making stars efficiently. The ionized universe was also easier to observe, at least in principle. Neutral hydrogen absorbs so many wavelengths of light that it acts like a fog, obscuring our view of what lies beyond. but ionized hydrogen is transparent to most wavelengths. This meant that structures forming after reionization would be more visible to us today when we look back across cosmic time with our telescopes. Let yourself imagine floating in this newly transparent universe, 700 or 800 million years after the Big Bang. In every direction you look, you can see the glow of young galaxies, each one a collection of massive stars, some already exploding as supernovae, enriching the cosmos with heavy elements. The universe is young, energetic, violent in its creativity. New stars are being born at prodigious rates. Dark matter continues pulling gas together into larger and larger structures. The stage is set for the next phase of cosmic evolution, the assembly of true galaxies. Rest for a moment. Breathe slowly. Let the enormity of these timescales wash over you without trying to fully grasp them. Hundreds of millions of years, each year a full orbit of a planet that doesn't exist yet around a star that hasn't formed. Time beyond human comprehension, and yet, to the universe, just the opening act. The first heavy elements. Before we talk about the first galaxies themselves, we need to understand one of the most important consequences of those first stellar generations. We need to talk about cosmic chemical enrichment, about how the universe went from having only 3 elements to having the full periodic table, all 92 naturally occurring elements from hydrogen to uranium. This process, often called metal enrichment in astronomical terminology, where metal means any element heavier than helium, fundamentally changed the rules of star and galaxy formation. It's hard to overstate how important this was. Without heavy elements, we wouldn't have planets, we wouldn't have chemistry, we wouldn't have life. Everything that makes the universe interesting beyond just hydrogen and helium came from stellar nucleosynthesis, from the forging of elements in stellar cores and supernova explosions. Let's trace this story element by element, starting with carbon. Carbon is created in the cores of massive stars when helium fusion begins. 3 helium nuclei come together through a process called the triple alpha process, fusing to form a carbon nucleus. This happens at temperatures around 100 million degrees, which only occurs in stars massive enough to compress their cores to these extreme conditions after they've exhausted their hydrogen fuel. The population 3 stars, with their enormous masses, would have been prodigious carbon producers. After a few million years of burning hydrogen into helium, they would begin helium fusion, building up carbon and oxygen in their cores. As they aged further, if they were massive enough, they would continue to heavier elements, carbon and oxygen fusing into neon and magnesium, neon fusing into silicon, silicon fusing into iron, each stage happening at higher temperatures, each stage proceeding faster than the last, until the star's core was an onion-like structure of nested shells, each shell composed of a different element. When these stars exploded as supernovae, all these elements were blasted into space. The explosion itself created even more elements through rapid nuclear reactions during the blast, elements heavier than iron, which can't be formed by normal fusion, were created through neutron capture during the supernova. Gold, platinum, uranium, all the elements that require neutron-rich environments were forged in these stellar deaths. The material ejected by supernovae didn't just sit there. It mixed with the surrounding gas, the pristine hydrogen and helium that had never been through a star. This mixing process wasn't uniform. Some regions received more supernova ejecta than others. Some regions might have been enriched by 1 or 2 supernova, while others experienced hundreds of supernova going off in a relatively small volume, leading to high metal concentrations. This metal enrichment had profound effects on subsequent star formation. Heavy elements, particularly carbon and oxygen, are much more efficient coolants than molecular hydrogen. A tiny amount of carbon or oxygen in a gas cloud can dramatically increase how quickly the cloud can radiate away heat. And remember, cooling is crucial for star formation. The more efficiently gas can cool, the lower the gene's mass becomes, which means smaller stars can form. There's a critical metallicity threshold that scientists have identified through modeling and observation. When gas reaches a metallicity of roughly 1/10,000th to 1/10,000th that of the Sun, dust grains can begin to form. These dust grains are incredibly efficient at cooling gas, radiating away heat as infrared light. Once dust cooling becomes effective, the minimum stellar mass drops dramatically. Instead of only forming stars dozens or hundreds of times the mass of the Sun, gas clouds can now form stars similar to our Sun or even smaller. This transition from population 3 stars to population 2 stars, stars with some heavy element content, marked a fundamental shift in cosmic evolution. Population 2 stars, because they could be smaller, lived longer. They were more diverse in their properties. Some were massive and short-lived, like population 3 stars, but others were moderate mass or low mass stars that could live for billions or even trillions of years. The first heavy elements also enabled the formation of molecules other than molecular hydrogen. Carbon monoxide, water, various organic molecules, all these became possible once carbon and oxygen were available. These molecules further enhanced cooling and also provided the raw materials for chemistry for complex molecular structures that would eventually, billions of years later, become the basis for life. Scientists can trace the history of metal enrichment by studying ancient stars in our own galaxy. The oldest stars in the Milky Way, found in the halo surrounding our galaxy, have very low metallicities, sometimes just 1,000th or 1/10,000th the metal content of the Sun. These stars formed from gas that had been enriched by only a few generations of supernovae. They're not quite as metal-free as population 3 stars, but they're close, and they provide a window into what stellar populations look like in the early universe. Intriguingly, despite decades of searching, astronomers have never found a confirmed population 3 star. Every star we've observed, even the most ancient ones we can find, has at least some small amount of heavy elements. This makes sense if population 3 stars were only the very first generation, if they lived such short lives that none have survived to the present day. But it's also possible, perhaps even likely, that population 3 stars continue forming even today in rare pockets of pristine gas. Recent observations with the James Webb Space Telescope have identified candidate galaxies that may harbor population 3 stars. One galaxy, named Amor 6, shows signatures consistent with extremely low metallicity. It was detected at a time when the universe was about 900 million to 1 billion years old. The galaxy shows strong hydrogen emission but no detected oxygen lines, which could suggest its gas is nearly pristine, though further observations are needed to confirm whether it's truly hosting metal-free star formation even at that relatively late epoch. This is surprising and exciting. the prevailing assumption had been that metal enrichment happened quickly, that after the first few 100 million years, essentially all gas would have been contaminated with heavy elements. But the universe is a big place, and it's possible there were regions, sheltered pockets, where pristine gas survived much longer than expected, or there may be mechanisms still being studied for stripping metals from gas, potentially cleaning it back to a primordial state and allowing population 3 star formation to occur multiple times in the same region. The discovery of Amor 6 and similar candidates suggests that the transition from population 3 to population 2 star formation may not have been a sharp cutoff, but rather a gradual transition that varied from place to place. In some regions, metal enrichment appears to have happened quickly, and population 2 stars dominated within a few 100 million years. In other regions, conditions may have conspired to preserve pockets of primordial gas for much longer. Breathe deeply and let this sink in. The universe, in its infancy, was teaching itself chemistry. Each generation of stars enriched the cosmos a little more, added a few more elements to the cosmic inventory, expanded the repertoire of what was possible. From 3 elements to 92, from the simplest possible chemistry to the complex molecular structures that would eventually enable planets and life. All of it traceable back to those first massive stars, those cosmic pioneers that burned briefly but changed everything. Assembly begins. Now we come to the heart of our story, with population 3 stars forming, with supernovae enriching the gas, with reionization gradually lighting up the universe. The stage was set for the first true galaxies to assemble. And this is where our story becomes even more remarkable, because what we thought we knew about early galaxy formation has been overturned by recent observations from the James Webb Space Telescope. Let's start with what theory predicted. Based on our understanding of dark matter, cosmic expansion, and structure formation, cosmologists expected the first galaxies to be small, faint, and rare. The logic was straightforward. In a hierarchical universe where small structures form first and then merge to build larger structures, the earliest galaxies should be the smallest ones, perhaps containing just 1 million or 10 million stars, much smaller than modern galaxies like the Milky Way with its 200 billion stars. Moreover, these first galaxies should form relatively late, perhaps not until 500 million years after the Big Bang or even later. Why? Because it takes time for gas to cool and collect in dark matter halos, time for stars to form, time for those stars to influence their surroundings. The first isolated massive stars might form at 100 or 200 million years, but assembling them into coherent gravitationally bound systems should take considerably longer. This is what theory predicted. This is what astronomers expected to find when JWST turned its powerful gaze toward the early universe. And this is not what they found. In July 2022, just days after JWST began its science operations, astronomers were stunned by what they saw. The telescope's first deep images revealed galaxies that appear to exist just 300 to 400 million years after the Big Bang. Not small, faint dwarf galaxies, but relatively bright, substantial systems. And as observations continued over the following months and years, the surprises multiplied. One of the earliest confirmed galaxies is nicknamed Maisie's Galaxy, scientifically designated CEERS 588. Spectroscopic observations, the gold standard for distance determination, confirmed that this galaxy existed just 390 million years after the Big Bang, when the universe was less than 3% of its current age. The galaxy is surprisingly bright, much brighter than models predicted galaxies should be at such early times. Another galaxy, CEERS 2588, existed just 410 million years after the Big Bang. JD's GSZ 14-0, currently one of the most distant confirmed galaxies, existed only about 300 million years after the Big Bang. This galaxy is particularly remarkable. Despite forming so early, it's large enough and bright enough to be detected by JWST from across 13.5 billion light-years of space and time. These discoveries raised immediate questions. How could galaxies form so quickly? How could they become so bright in such a short time? The surprise wasn't just that galaxies existed at these early epochs. The surprise was how massive and luminous they initially appeared to be. Some early estimates, based on preliminary photometric data, suggested these galaxies contained stellar masses equivalent to 1 billion suns or more, which seemed to challenge our understanding given the limited time available for star formation. For a brief period, there was talk of a cosmological crisis, of whether these observations might require revising our understanding of the Big Bang, dark matter, or cosmic expansion. Some researchers worried that the standard model of cosmology, the lambda cold dark matter model that has been so successful at explaining most observations, might need to be thrown out or substantially modified. But as often happens in science, the resolution was more subtle than the initial panic suggested. More detailed observations, particularly spectroscopic studies that could measure galaxy properties more accurately, revealed what was actually going on, and it's a fascinating story that teaches us about both early galaxies and the pitfalls of interpreting limited data. First, many of the initial distance estimates were based on photometry alone, measuring how bright galaxies appear in different filters and using those colors to estimate distance. This technique works well most of the time, but it can be fooled. When spectroscopy was obtained for some of these candidate distant galaxies, it turned out they were actually much closer and much less remarkable than initially thought. One famous case, a galaxy initially called CEERS 93316, was thought to be at a redshift of 16, corresponding to just 250 million years after the Big Bang. Follow-up spectroscopy revealed it was actually at a redshift of only 4.9, still distant but nowhere near as extreme. So some of the apparently impossible galaxies turned out to be ordinary galaxies at more reasonable distances. But not all of them. Many of the brightest early galaxy candidates have been confirmed as genuinely ancient and genuinely bright. So the question remains, how did they form so quickly and become so luminous? The answer appears to involve black holes. When researchers obtained detailed spectra of some of these bright early galaxies, they found signatures of rapidly moving gas, characteristic of material swirling around supermassive black holes. These galaxies weren't necessarily as massive as they initially appeared. Instead, much of their light was coming from active galactic nuclei, from black holes actively feeding on surrounding gas and releasing tremendous energy in the process. This revelation was important. Black holes can produce far more light per unit mass than stars can. A relatively modest galaxy with an active black hole at its center can appear as bright as a much more massive galaxy composed purely of stars. When researchers accounted for the contribution from black holes, the apparent stellar masses of these early galaxies dropped considerably, bringing them back into line with theoretical expectations. This doesn't mean the mystery is completely solved. Even accounting for black holes, these early galaxies are still more numerous and brighter than the most conservative models predicted. The universe appears to have been remarkably efficient at forming stars and galaxies in its first few 100 million years. Star formation rates were higher than expected. Gas was converting into stars more efficiently than in the modern universe. Several factors might explain this enhanced efficiency. The gas in the early universe was pristine, uncontaminated by heavy elements for the first few generations of stars. Perhaps metal-free or metal-poor gas is actually more efficient at forming stars under the right conditions. The early universe was also denser, which meant gas clouds in early galaxies experienced stronger gravitational forces, potentially leading to more rapid collapse and star formation. The role of dark matter halos is also crucial. The first galaxies formed in dark matter halos that were rapidly growing through mergers and accretion. This growth provided a steady supply of fresh gas falling into the galaxies, fueling continuous star formation. In the modern universe, many galaxies have exhausted their gas supplies or have their gas supplies cut off by various processes. But in the early universe, the gas was still abundant and actively funneling into growing halos. Observations with JWST have also revealed something unexpected about the shapes and structures of early galaxies. Modern galaxies come in two main types: spirals like the Milky Way, with rotating disks and spiral arms, and ellipticals with more spheroidal shapes and no organized rotation. The earliest galaxies observed by JWST don't fit neatly into either category. Many appear to have flattened oval disk shapes or irregular, clumpy morphologies. Some look like tubes or elongated structures. They're messy, chaotic, still in the process of assembling themselves. This makes sense if galaxy formation was still in its early stages. These galaxies hadn't had time to settle into stable configurations. They were actively merging, accreting gas, forming stars in bursts rather than steadily. The universe at these early times was a violent, dynamic place, very different from the more settled cosmos we see around us today. Let your mind rest with that image for a moment. Hundreds of millions of years after the Big Bang, the universe filled with these small, bright, chaotic galaxies, each one a cauldron of star formation, with massive stars being born and dying on timescales of millions of years. Black holes growing at the centers of these galaxies, fed by abundant gas, occasionally flaring into brilliance. Galaxies colliding and merging, their stars and gas mixing together to form larger systems. All of this happening in a universe that was still mostly ionized hydrogen, still expanding and cooling, but now increasingly structured, increasingly complex. The cosmic web emerges. As the first galaxies assembled, they weren't distributed randomly through space. They followed a pattern, a structure that was laid down by dark matter in the hundreds of millions of years after the Big Bang. They traced out the cosmic web, that intricate network of filaments, walls, and nodes that defines the large-scale structure of the universe. Understanding the cosmic web requires stepping back to see the universe at its largest scales. Imagine you could zoom out from the Milky Way, out past our local group of galaxies, out past the Virgo cluster, out to scales of hundreds of millions of light years. What you'd see is not a uniform distribution of galaxies. You'd see structure. Galaxies cluster together into groups and clusters. These clusters are connected by filaments, long strands where galaxies line up like beads on a string. The filaments and clusters enclose voids, vast, nearly empty regions where few galaxies exist. This cosmic web structure emerges naturally from gravitational instability acting on the initial density fluctuations present in the early universe. Remember those tiny variations we talked about? 1 part in 100,000 differences in density revealed by the cosmic microwave background. Those variations weren't spherical. They were anisotropic, meaning they had different strengths in different directions. Some regions were overdense along one axis but average along others. Others were overdense along 2 axes, forming sheet-like structures. When gravity acts on these anisotropic perturbations, they collapse differently depending on their shape. A perturbation overdense in 3 dimensions collapses into a roughly spherical node. A perturbation overdense in 2 dimensions collapses into a sheet or wall. A perturbation overdense in 1 dimension collapses into a filament, and regions that are underdense expand faster than the average, becoming voids. This process, described mathematically by what's called the Zeldovich approximation, predicts that the universe should naturally organize into a web-like structure of walls, filaments, and nodes separated by voids. And this is exactly what we observe. Computer simulations that start from initial conditions matching the cosmic microwave background and follow the evolution of dark matter under gravity produce cosmic webs that look remarkably similar to what we see in galaxy surveys. The cosmic web isn't static, it's constantly evolving. Matter flows from voids into walls, from walls into filaments, from filaments into nodes. Galaxies forming in filaments tend to move along the filaments toward nodes, where they eventually join galaxy clusters. This flow pattern is one of the defining features of hierarchical structure formation. The idea that small structures form first and merge to build larger structures over time. Think about this flow for a moment. A galaxy forming in a void, a relatively rare occurrence, experiences weak gravity from all directions, pulling it gently in multiple directions at once. But a galaxy forming near a filament feels stronger gravitational attraction toward the filament. Over millions and billions of years, it drifts toward the filament, accelerating as it gets closer. Once it reaches the filament, it begins flowing along the filament toward the nearest node, like water flowing through a cosmic river system toward the ocean. This motion isn't smooth and steady. Galaxies don't flow serenely through space. They tumble and rotate as they move. They interact with other galaxies also flowing along the same filament. They experience gravitational interactions with the dark matter surrounding them. Their paths are complex, chaotic in the technical sense, sensitive to small variations in initial conditions, and yet, statistically, averaged over many galaxies. The pattern is clear. Matter flows from low-density to high-density regions, concentrating over time into ever denser nodes. In the early universe, during the first billion years after the Big Bang, the cosmic web was just beginning to take shape. The filaments were thinner, less defined than they are today. The nodes were smaller, containing what would eventually become the first galaxy clusters, but in their infancy. The contrast between dense and empty regions was less extreme, but the basic pattern was already there, laid down by dark matter waiting for galaxies to form and light it up. The first galaxies formed preferentially in the densest regions, along filaments and at nodes where filaments intersected. This makes intuitive sense. Dense regions have stronger gravity, which means gas falls into them more readily and can cool and form stars more efficiently. The first dark matter halos to reach the mass needed for efficient star formation were the ones in overdense regions. Moreover, galaxies in dense regions had more opportunities for interactions. When two galaxies in a filament passed near each other, they could gravitationally influence each other's gas, potentially triggering bursts of star formation. They could merge, combining their mass and creating larger systems. This frequent interaction and merging in dense regions led to faster galaxy growth compared to isolated galaxies in underdense regions. This led to a sort of cosmic feedback loop. Galaxies forming in overdense regions enriched their surrounding gas with heavy elements through supernova explosions. This enriched gas made it easier for subsequent generations of stars to form. Meanwhile, the ultraviolet radiation from these galaxies ionized the gas around them, affecting how gas could flow into neighboring regions. Dense regions where star formation had started tended to continue forming stars more readily than underdense regions where star formation had not yet begun. Over hundreds of millions of years, this led to increasing concentration of galaxies along filaments and at nodes. By the time the universe was 1 billion years old, the cosmic web was clearly visible in the distribution of galaxies, and today, 13.8 billion years after the Big Bang, the cosmic web dominates the large-scale structure of the universe. Modern galaxy surveys have mapped this structure in exquisite detail. The Sloan Digital Sky Survey, for instance, has measured the positions and distances of hundreds of thousands of galaxies, revealing the cosmic web across a significant fraction of the observable universe. When you look at these maps, you see filaments that can stretch for hundreds of millions of light years, with galaxies densely packed along them. You see walls, sheet-like structures that enclose voids, and you see voids themselves, vast, emptied-out regions containing only a handful of galaxies. The cosmic web also influences how galaxies evolve. Galaxies in different environments, in dense filaments versus sparse voids, for instance, have different properties. Galaxies in filaments tend to be redder, meaning they have older stellar populations and lower rates of ongoing star formation. Galaxies in voids tend to be bluer, actively forming stars. This suggests that environment plays a role in regulating star formation, perhaps through effects on gas supply or through interactions with neighboring galaxies. Even the shapes of galaxies correlate with the cosmic web. Studies have found that the spins of spiral galaxies tend to align parallel to nearby filaments, while elliptical galaxies have their spins perpendicular to filaments. These alignments tell us something about how galaxies acquired their angular momentum, how they formed and evolved in the context of their large-scale environment. The cosmic web is also important for cosmology, for testing our theories of dark matter and dark energy. The pattern of the cosmic web, the sizes of voids, the lengths and thicknesses of filaments. All these properties depend on cosmological parameters like the total amount of dark matter, the strength of dark energy, the initial spectrum of density fluctuations. By measuring the cosmic web in detail, astronomers can constrain these parameters and test whether our cosmological models are correct. Recent studies have even begun detecting the gas in the cosmic web directly. Most of the gas in filaments is too diffuse and too hot to form stars. It exists as ionized plasma, heated by shocks and by radiation from galaxies. This warm, hot intergalactic medium, as it's called, is difficult to observe because it doesn't emit much light, but it absorbs light from background quasars in characteristic ways, leaving absorption lines in quasar spectra that reveal where the gas is and how much there is. Observations of these absorption lines suggest that a substantial fraction of the universe is ordinary matter. Current estimates indicate perhaps 30 to 40% or more resides in this warm, hot phase in the cosmic web filaments. This is matter that's not in galaxies, not in stars or gas clouds, but in the space between galaxies, threading the cosmic web. It represents the fuel that will eventually feed the next generations of star formation as it continues to flow along filaments into galaxies. Rest now, breathe slowly. Picture the cosmic web stretching across the universe, a structure so vast that light takes billions of years to traverse it, and yet a structure that started from variations so tiny they could barely be measured. From fluctuations of 1 part in 100,000 to a web spanning billions of light years. This is the power of gravity, the power of time, the power of simple physical laws acting on cosmic scales. Diversity from uniformity. One of the most profound questions in cosmology is how the enormous diversity of galaxies we see today arose from the nearly uniform conditions of the early universe. Why are some galaxies spirals while others are ellipticals? Why do some galaxies form stars vigorously while others are quiescent? Why do galaxies range in size from dwarfs with a few million stars to giants with trillions of stars? The answer lies in the complex interplay of initial conditions, environment, and the stochastic nature of galaxy formation and evolution. Let's start with galaxy types. In the modern universe, we categorize galaxies into several main types. Spiral galaxies, like the Milky Way and Andromeda, have rotating disks of stars and gas with prominent spiral arms. They're often actively forming new stars, particularly in their spiral arms where gas is compressed. Elliptical galaxies are more spheroidal, lacking organized rotation, typically containing older stars with little ongoing star formation. Irregular galaxies have chaotic structures without clear symmetry, often driven by recent mergers or interactions, and there are various intermediate types and subtypes within this classification scheme. In the early universe, as we've discussed, JWST observations show that galaxies had different morphologies than today. They were clumpier, more irregular, often showing multiple bright knots of star formation. Many had elongated or flattened shapes that don't fit neatly into our modern classification scheme. This suggests that modern galaxy types emerged over time as galaxies evolved and settled into more stable configurations. How does this evolution happen? Primarily through a combination of internal processes and external interactions. Let's start with internal processes. When a galaxy forms stars, those stars affect their environment through stellar feedback. Massive stars produce strong stellar winds and eventually explode as supernovae, injecting enormous amounts of energy into the surrounding gas. This energy can heat gas, making it harder to form more stars. It can drive gas out of the galaxy entirely in powerful winds, or it can compress gas in some regions while dispersing it in others, affecting where and how quickly future star formation occurs. Black holes at galaxy centers provide another form of feedback. When a supermassive black hole actively feeds on surrounding gas, it releases tremendous energy, often much more than all the stars in the galaxy combined. This energy, in the form of radiation and powerful jets, can heat gas throughout the galaxy, suppressing star formation. Many massive galaxies appear to have had their star formation quenched by black hole feedback, transitioning them from actively star-forming blue galaxies to quiescent red galaxies. External interactions are equally important. When galaxies pass close to each other, their gravitational fields interact. This can trigger bursts of star formation by compressing gas clouds. It can distort galaxy shapes, pulling out long tidal tails of stars and gas. If the encounter is close enough or slow enough, the galaxies can merge entirely, combining their stars, gas, and dark matter into a single, larger system. Galaxy mergers are particularly important for understanding how modern galaxy types formed. Computer simulations suggest that when two spiral galaxies merge, the result is often an elliptical galaxy. The organized rotation of the spiral disks gets disrupted by the merger, and the stars end up on more random orbits, creating the spheroidal shape characteristic of an elliptical. Many of the giant elliptical galaxies we see today are thought to have formed through multiple mergers of smaller galaxies over billions of years, though the detailed history of each galaxy remains unique. The environment in which a galaxy resides also plays a crucial role. Galaxies in dense environments, like galaxy clusters, interact with their neighbors more frequently than isolated galaxies in voids. They also experience ram pressure stripping, where the hot gas filling the space between galaxies in a cluster strips gas out of a galaxy moving through it, much like a headwind blowing papers off a car. This can shut down star formation by removing the galaxy's fuel supply. Galaxies in clusters also experience a process called galaxy harassment, where repeated high-speed encounters with neighboring galaxies gradually transform their morphology and star formation properties. Even without direct collisions, the tidal forces from these encounters can heat up the galaxy's disk, puffing it up and making it more spheroidal over time. The hierarchical nature of structure formation means that galaxy growth happens over extended periods through many small accretion events and occasional major mergers. A typical large galaxy like the Milky Way didn't form in one step. It assembled gradually over billions of years, accreting smaller dwarf galaxies, pulling in streams of gas from the cosmic web, occasionally merging with other galaxies of comparable size. The Milky Way is currently in the process of consuming several small dwarf galaxies. Based on current measurements of its motion, Andromeda appears to be on a collision course with the Milky Way, with the two galaxies predicted to merge in about 4 billion years. This hierarchical assembly has observational consequences. When astronomers look at galaxies at different distances, corresponding to different cosmic times, they see systematic differences. Galaxies in the distant past were generally smaller, more gas-rich, more actively star-forming, and more irregular than galaxies today. This is exactly what we'd expect if galaxies grow over time through mergers and accretion. The initial conditions matter too. We mentioned that the cosmic web creates different environments, and galaxies forming in different parts of the web have different evolutionary paths. But even within a given environment, there's randomness. The exact timing of when a dark matter halo reaches critical mass for star formation, the exact configuration of smaller halos that merge to form a larger halo, the exact locations and numbers of supernovae that enrich a galaxy's gas, all these details vary from galaxy to galaxy and affect the final outcome. This stochastic variation means that even galaxies with similar masses in similar environments can have different properties. Two galaxies might form in halos of identical mass, but if one experienced an early major merger that triggered a burst of star formation, while the other grew gradually through smaller accretions, they could end up looking very different today. JWST observations are revealing the early stages of this diversification. Even in the first billion years after the Big Bang, galaxies showed a range of properties. Some were compact and concentrated, others were extended and diffuse. Some showed ordered rotation, others appeared chaotic. This early diversity set the stage for the rich variety of galaxy types we see in the modern universe. One particularly interesting finding from JWST is the presence of disk-like structures in some very early galaxies. Previously, it was thought that disks, the rotating structures characteristic of spiral galaxies, took a long time to form and wouldn't be common in the early universe. But JWST has found galaxies with clear, disk-like morphologies at redshifts corresponding to just a few 100 million years after the Big Bang. This suggests that the angular momentum needed to form rotating disks was present early, and that disk formation was a rapid process. Another surprise is the presence of what appear to be bars in some early galaxies. Bars are elongated structures in the centers of spiral galaxies thought to form through gravitational instabilities in rotating disks. Their presence in very young galaxies suggests that even early on, galaxies were dynamically mature enough to develop these complex structures. As you lie there, breathing slowly, let yourself appreciate the complexity that has emerged. The universe started with almost perfect uniformity, just tiny variations from place to place. And from that uniformity, through the action of gravity, through the physics of star formation and galaxy evolution, through the randomness of mergers and interactions, an incredible diversity emerged. Every galaxy tells a different story, has a different history, formed through a unique sequence of events that can never be exactly repeated. And yet all of them, every single one, trace their lineage back to those tiny fluctuations in the early universe, to the same simple physical laws acting over billions of years. The unexpected abundance. Let's return to one of the central puzzles raised by JWST observations. Why are there so many bright galaxies in the early universe? Why do we see more luminous galaxies, more massive galaxies forming earlier than our models predicted? This question has driven a tremendous amount of research over the past few years, and while we don't have all the answers yet, we're beginning to understand what's going on. The surprise wasn't just that galaxies existed early. As we've discussed, theorists expected galaxies to start forming a few 100 million years after the Big Bang. The surprise was how bright these early galaxies were. When astronomers calculated how many high-luminosity galaxies should exist at various redshifts based on our standard cosmological model, they predicted very few bright galaxies at redshifts above about 10, corresponding to earlier than 500 million years after the Big Bang, but JWST found them in abundance. To understand why this was surprising, we need to understand how galaxy luminosity relates to galaxy mass and star formation. A galaxy's luminosity comes primarily from its stars. The more stars a galaxy has, especially young, massive, bright stars, the more luminous it is. And building up a large stellar mass takes time. Stars form from gas, and there's only so much gas available in a given dark matter halo, and that gas can only be converted to stars so quickly. In the standard model, star formation efficiency, the fraction of available gas that gets turned into stars per unit time, was thought to be relatively constant or to vary in predictable ways. Early galaxies should have been forming stars, but not so efficiently that they could build up huge stellar masses in just a few 100 million years. Yet that's what some of the JWST observations seem to show, at least initially. As we mentioned earlier, one resolution came from recognizing the role of black holes. Many of the brightest early galaxies have active galactic nuclei, black holes at their centers that are actively feeding and producing enormous amounts of light. When researchers carefully separated the light from stars versus the light from active galactic nuclei, the stellar masses of these galaxies dropped to more reasonable values. The galaxies weren't as massive as they initially appeared. They were just being brightened by their central black holes. But this wasn't the complete answer. Even accounting for black holes, there were still more early galaxies than the most conservative models predicted. Something about star formation in the early universe must have been different, more efficient, or more vigorous than in the modern universe. Several factors might contribute to this enhanced star formation. One is the nature of the gas itself. Early in cosmic history, before many generations of stars had lived and died, gas had lower metallicity, fewer heavy elements. Metal-poor gas might have different cooling properties or different responses to stellar feedback, potentially allowing more efficient star formation under certain conditions. Another factor is gas supply. Early galaxies were embedded in rapidly growing dark matter halos that were actively accreting gas from their surroundings. Unlike many modern galaxies, which have exhausted their gas supplies or had their gas stripped away by environmental processes, early galaxies had abundant fuel for star formation. The gas was continuously flowing in from the cosmic web, feeding ongoing star formation. The mode of star formation might also have been different. In the modern universe, star formation tends to be relatively steady over time, regulated by feedback processes that balance gas inflow and star formation and gas outflow. But in the early universe, star formation might have been burstier, with periods of intense star formation alternating with quiescent periods. During the bursts, star formation rates could be much higher than the average, making galaxies appear very bright when observed during a burst phase. This remains an area of active investigation. This bursty star formation could arise from several causes. Gas accretion from the cosmic web might be clumpy rather than smooth, with large clouds of gas periodically falling into the galaxy and triggering bursts of star formation. Galaxy mergers, which were more common in the dense early universe, could also trigger bursts. Even internal instabilities in the galaxy's gas disk could lead to episodic star formation. Computer simulations exploring these possibilities have shown that models with bursty star formation can indeed produce more bright galaxies at early times than models with steady star formation. The key is that during a burst, a galaxy can be much brighter than its average luminosity over time. So if JWST happens to observe galaxies preferentially during their burst phases, which might be more likely because that's when they're brightest and easiest to detect, it would see more bright galaxies than predicted by models assuming constant average star formation rates. The efficiency of converting gas into stars might also have been higher in the early universe. In the modern universe, various feedback processes from stellar winds and supernovae to black hole-driven outflows expel a significant fraction of a galaxy's gas before it can form stars. Typical star formation efficiencies in modern galaxies are around a few percent, meaning only a few percent of the available gas gets turned into stars before the rest is ejected or heated to temperatures where it can't collapse. But perhaps in the early universe, before feedback processes had time to fully establish themselves, or in the specific conditions of rapidly accreting gas-rich early galaxies, star formation efficiency was higher. If 10 or 20% of the gas could be converted to stars instead of just a few percent, galaxies could build up stellar mass much more quickly. Recent theoretical work has developed what's called a constant star formation efficiency model. This model assumes that the efficiency of turning gas into stars was roughly constant over cosmic time. But because dark matter halos were growing rapidly in the early universe, providing a continuous supply of fresh gas, the absolute star formation rates could be very high. This model has been quite successful at matching JWST observations without requiring fundamentally new physics. There's also the question of the initial mass function, the distribution of stellar masses when stars form. In the modern universe, for every massive bright star that forms, many lower mass dimmer stars also form. The initial mass function is weighted toward low-mass stars, but it's possible that in the early universe, with its different gas conditions, the initial mass function was different, potentially skewed toward more massive stars. This would make early galaxies appear brighter for a given stellar mass, though confirming this requires more observations. We've already discussed population 3 stars, which theoretical models predict were certainly weighted toward high masses. But even after the transition to population 2 star formation with metal-enriched gas, the initial mass function might have remained somewhat top-heavy for a while, based on some models, potentially shifting toward the modern distribution over hundreds of millions of years as conditions evolved. All of these factors, bursty star formation, high star formation efficiency, top-heavy initial mass functions, abundant gas supply, likely work together to explain the JWST observations. The early universe was a special time, a time when conditions favored rapid galaxy growth and bright young galaxies. As the universe aged, as gas supplies dwindled, as feedback processes became more effective, as metals accumulated in the gas, galaxy formation settled into a different mode, the mode we see in the modern universe. What's remarkable is that despite the initial surprise and confusion, despite talk of a cosmological crisis, the observations ultimately reinforced our standard model rather than breaking it. The lambda cold dark matter cosmology, with its specific amounts of ordinary matter, and dark energy, still works. We just needed to refine our understanding of how baryonic physics, the physics of ordinary matter, operates in the specific conditions of the early universe. This is how science progresses. Observations challenge models. Models are refined to match observations. New predictions are made. New observations test those predictions. The cycle continues, spiraling toward deeper understanding. JWST's discoveries about early galaxies are refining our models of galaxy formation, teaching us about star formation physics, about feedback processes, about gas dynamics in the early universe, and future observations. As JWST continues its mission and as next-generation telescopes come online, we'll continue this process. Let yourself relax deeper now. The universe is vast and complex, full of mysteries we're only beginning to unravel. But there's beauty in that mystery, comfort in knowing that there's always more to discover, more to understand. The first galaxies, those bright young systems lighting up the early universe, are no longer quite as mysterious as they were just a few years ago. We're beginning to understand their story, but there's still so much more to learn. Legacy and connection. As we near the end of our journey, let's talk about connection, about legacy, about how those first galaxies from billions of years ago relate to us here and now. Because this isn't just ancient history we're discussing. This is our history, our origins, the story of how the universe became capable of producing planets and life and consciousness. Every galaxy we see today, including our own Milky Way, traces its lineage back to those early times. The Milky Way formed through the gradual merger and accretion of many smaller galaxies over billions of years, a history we've pieced together through observations of ancient stars and computer simulations. Some of those progenitor galaxies likely were among the first to form, lighting up when the universe was just a few 100 million years old. Their stars, their gas, their dark matter, all of it eventually found its way into the structure we call home. We can actually observe some of this history. The Milky Way contains ancient stars, found primarily in its halo and in globular clusters that formed billions of years ago in smaller galaxies that later merged with our own. By studying these stars, their ages, their compositions, their orbits, astronomers can reconstruct pieces of the Milky Way's assembly history. They can identify streams of stars that came from particular dwarf galaxies that fell into the Milky Way at specific times. They can trace back the galaxy's growth over cosmic time. One particularly ancient feature of the Milky Way is a component called the thick disk, a layer of old stars above and below the main galactic plane. These stars formed early in the Milky Way's history, possibly during or shortly after major mergers that heated up the galaxy's disk. They're a fossil record of violent events in our galaxy's youth, preserved across billions of years. The oldest stars in the Milky Way, with ages of 13 billion years or more, formed when the universe itself was less than 1 billion years old. These stars, with their very low metallicities and their high velocities, are relics of the early universe, messengers from cosmic dawn who have survived across almost the entire history of the cosmos. When we study these stars, we're directly observing material that has barely changed since the first few 100 million years after the Big Bang. But the connection goes deeper than just the Milky Way's history. The atoms in your body, the carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of these elements were forged in stars. Many of them were likely created in those very early generations of stars we've been discussing, the first supernovae exploding just a few 100 million years after the Big Bang, ejected heavy elements into the cosmos. Those elements, mixed with surrounding gas, were incorporated into later generations of stars, were processed further, ejected again, recycled multiple times over billions of years, until eventually they found their way into the molecular cloud that collapsed to form our solar system. Think about that for a moment. The atoms in your body are older than Earth, older than the Sun, older than the Milky Way in its current form. They've been through multiple stellar lifetimes, created in fusion reactions, scattered by supernovae, drifting through space, falling into new stars, being ejected again. Each atom in your body has a cosmic history stretching back billions of years. When we study the first galaxies, we're studying the beginning of this process of cosmic chemical enrichment that made our existence possible. Without those early generations of massive stars, without the supernova that scattered heavy elements through the universe, there would be no carbon for organic chemistry, no oxygen for water, no silicon for rocks, no iron for planetary cores. The universe would still be just hydrogen and helium, incapable of producing the chemical complexity necessary for life. The structure of the universe also matters for our existence. We exist in a galaxy that's part of a larger structure, the local group, which is itself part of a filament in the cosmic web. Our position in this structure affects the galaxy's evolution, the rate at which new stars form, the stability of planetary systems. If the Milky Way had formed in a different environment, in the center of a massive galaxy cluster, for instance, conditions would be very different. The galaxy might have lost most of its gas to ram pressure stripping, shutting down star formation billions of years ago. In that case, our solar system might never have formed, or would have formed much earlier when conditions were less favorable for life. The timing matters too. We exist roughly 13.8 billion years after the Big Bang, about 9.2 billion years after the Sun and Earth formed. This is probably not a coincidence. Earlier in cosmic history, the universe was more violent, with more frequent supernovae, more intense radiation from quasars, more frequent galaxy mergers. These conditions might have been hostile to the development of complex life. The universe needed time to settle down, for heavy elements to accumulate to levels sufficient for planet formation, for galaxies to mature into more stable environments. There's a concept in cosmology called the Copernican principle, the idea that we shouldn't consider ourselves special or privileged in cosmic terms. We're not at the center of the universe. We're not in a unique galaxy or a unique location, but there's a related idea called the anthropic principle, which observes that the universe we see must be compatible with our existence as observers. We necessarily find ourselves in a time and place where conditions allow for life and consciousness, because if conditions didn't allow for that, we wouldn't be here to observe anything. This principle is sometimes debated among scientists and philosophers, but it offers one perspective on why we observe the universe in its current state. This doesn't mean the universe was designed for us or that we're the purpose of cosmic evolution. It just means that in a vast universe with enormous variation in conditions across space and time, observers like us will naturally find themselves in regions and epochs where conditions are favorable for life. The first galaxies, forming in the violent early universe, were not hospitable places for life, but they set in motion the processes that would eventually, billions of years later, create environments where life could arise. When you look up at the night sky, when you see the stars, you're seeing light that has traveled across space for years, decades, centuries, sometimes thousands or millions or even billions of years. You're looking back in time. The further you look, the further back you see, until at the very edge of the observable universe, you'd be seeing light from the first galaxies, the first stars, the very beginnings of cosmic structure. With JWST, astronomers can now see that far. They can observe galaxies as they were 13 billion years ago or more. They can watch cosmic dawn unfold. They can trace the evolution of galaxies from their chaotic early forms to the more settled structures we see nearby. In a very real sense, JWST is a time machine, allowing us to witness our cosmic origins, to see the universe when it was young and still finding its form. There's something profoundly moving about this capability. We're small, ephemeral beings on a tiny planet orbiting an ordinary star in an unremarkable galaxy. Our individual lives span at most a century, yet through science, through careful observation and thought, we can understand processes that unfold over billions of years. We can comprehend scales from subatomic particles to the entire observable universe. We can trace our origins back to the Big Bang itself. Breathe slowly now. Feel the weight of your body, the air moving through your lungs, the steady beating of your heart. You are a part of this story. The universe, through billions of years of evolution, has become capable of looking back at itself, of understanding its own history. You are the universe become conscious, contemplating its origins, marveling at the journey from simple beginnings to profound complexity. Peaceful conclusion. We've traveled a long way together tonight, from the darkness after the Big Bang, through the formation of the first stars, through cosmic reionization, through the assembly of the first galaxies, through the emergence of the cosmic web, to the connection between those ancient events and our present existence. It's a story of transformation, of how chaos and randomness and simple physical laws, acting over billions of years, created the breathtaking beauty and complexity we see around us. The universe didn't have to be this way. The fundamental constants of nature, the strength of gravity, the mass of the electron, the speed of light, all these values could have been different. And if they had been even slightly different, the universe would look completely different. Galaxies might not form. Stars might not be stable. Heavy elements might not be created. We exist in a universe that, by chance or necessity we don't fully understand, has properties that allow for richness, for structure, for life. The first galaxies, those bright young systems that formed when the universe was less than 1 billion years old, were the pioneers. They were the first organized structures larger than individual stars, the first systems capable of sustaining star formation over extended periods, the first to build up substantial populations of stars and begin the process of chemical enrichment that would eventually enable planets and life. They were messy, chaotic, irregular, still finding their forms. They merged and interacted, they grew and evolved. Over billions of years, they transformed into the diverse population of galaxies we see today. Some became great spirals like the Milky Way and Andromeda. Some became giant ellipticals, massive systems with trillions of stars. Some remained small dwarf galaxies scattered through space. But all of them, every single one, carries echoes of those early days, of cosmic dawn, of the time when the universe was young and the first galaxies were just beginning to shine. There's beauty in this story, but also mystery. We don't have all the answers. We don't fully understand dark matter. We can't yet observe population 3 stars directly. We're still refining our understanding of how galaxies form and evolve. The universe continues to surprise us, to challenge our models, to reveal new wonders with each new generation of telescopes. And that's okay. That's part of the beauty. We don't need to understand everything completely to appreciate the majesty of it all. Sometimes it's enough just to contemplate the enormity of cosmic time, the vastness of cosmic space, the intricate dance of matter and energy that has brought us to this moment. Let yourself rest now. Feel your body relaxing, your breathing slowing, your mind drifting. The universe has been here for 13.8 billion years. The first galaxies formed almost 13.5 billion years ago. Compared to these timescales, your worries, your stresses, the things that occupy your daily thoughts, they're fleeting, ephemeral, like ripples on the surface of a vast ocean. There's something comforting in that perspective. Your problems are real, of course. They matter in the context of your life, but set against the backdrop of cosmic history, there's a sense of scale, a reminder that the universe is ancient and vast, that it has witnessed the rise and fall of countless generations of stars, the formation and evolution of trillions of galaxies, the endless dance of matter through space and time. You are part of this dance. You're made of atoms forged in stellar cores and scattered by supernovae. You're standing on a planet formed from the debris of previous stars, orbiting a star in a galaxy built from the merger of countless smaller galaxies over billions of years. You are, in the most literal sense, star stuff contemplating itself. The universe become aware. Let that thought settle over you like a warm blanket. You belong here. You're part of the cosmic story. The journey from the first galaxies to you, from chaos to beauty, from simplicity to complexity, it's all connected. You're a product of billions of years of cosmic evolution, and that makes you, in your own way, as remarkable as any galaxy. If you found value in this journey tonight, if these ideas have sparked your curiosity or brought you peace, I'd be grateful if you take a moment to like this video and subscribe to the channel. Your support helps me continue creating these explorations of the cosmos, these journeys into the depths of space and time. There's so much more to discover, so many more stories to tell. But for now, rest. Let your mind drift where it will. You might think about dark matter halos forming in the early universe, patient and invisible. You might imagine the first massive stars igniting, lighting up the darkness for the first time. You might picture galaxies merging and growing over billions of years, building the structures we see today. Or you might just let these thoughts fade away, replaced by the gentle descent into sleep. The universe waited billions of years for galaxies to form, for stars to create heavy elements, for planets to coalesce, for life to arise, for consciousness to emerge. It waited for you, and now, having told you this story, having shared this journey through cosmic time, the universe invites you to rest. Close your eyes if they're not already closed. Feel the darkness behind your eyelids, not so different from the cosmic darkness before the first stars formed. But you're not in darkness alone. You're surrounded by light, by the knowledge of billions of galaxies, by the understanding of deep cosmic history, by the connection to everything that is and was and will be. Breathe, rest, dream if dreams come, and know that when you wake, the universe will still be here, still vast, still mysterious, still beautiful, still waiting for us to understand it a little better, to appreciate it a little more deeply, to marvel at the journey from chaos to beauty that brought us all into being. Thank you for joining me on this journey. Sleep well